Inspired by natural organisms like vines that cover the distance by growing, researchers at Stanford University have created a soft tubular robot that lengthens to explore hard-to-reach areas. A thick tendril snakes its way across a desk. It turns sharply, heading up to wrap its single tube-like appendage around a valve that moves slowly under its pressure. Though it looks like the work of a sentient vine, it's actually a robot, a soft plant-inspired creation that grows as a form of movement. So in this video, we're going to tell you inside look the life-saving unstoppable robot. The video is going to be amazing, so make sure you stick till the end. Before starting the video, be sure to smash that like button and subscribe to never miss out on any of our videos. A new class of continuum robots has recently been explored, characterized by tip extension, significant length change, and directional control. Here we call this class of robots vine robots due to their similar behavior to plants with the growth habit of trailing, tip-extending soft robots, taking flexible film or rubber as body material and fluid pressure as input power, exhibit excellent advantages in constrained and cluttered environments for detection and manipulation. However, existing soft continuum robots are of great challenges in achieving multiple, mutually independent and on-demand active steering over a long distance without precise steering control. Until now, however, they have not been deployed outside the lab. There are three features that are key for successful deployment in the field. The first is portability, second is the ability to be guided over long enough distances to be useful for navigation, third is intuitive human-in-the-loop teleoperation, which enables movement in unknown and dynamic environments. The vine-like robot can grow across long distances without moving its whole body, which could prove useful in search and rescue operations and medical applications. For example, the small airtight cylinder can be placed at the entrance of disaster site debris, and with the flip of a switch, a tendril extends from one end of the cylinder into the mass of stones and dirt like a fast-climbing vine. A camera at the tip of the tendril gives rescuers a view of the otherwise unreachable places beneath the rubble. The Stanford researchers have made a proof of concept of their soft-growing robot and have run it through some challenging tests. Essentially, we're trying to understand the fundamentals of this new approach to getting mobility or movement out of a mechanism, explained researcher Alison Okamura, a Stanford professor of mechanical engineering. It's very different from the way that animals or people get around the world. According to a paper published by the journal Science Robotics, one of these robots can extend from its tip to thousands of times its original body length at a speed comparable to animal and robotic locomotion. Scientists have already built robots that look like hell monster dogs, but there's something unnerving about this particular version of tentacle-like creeping. Soft robots have great advantages such as dexterous movement behavior, unprecedented adaptation, and extremely high security for inspection and exploration work in constrained, uncharted, and cluttered environments. Among the different types of soft robots, soft continuum robots, which are designed based on the principle of vine growth, have attracted significant attention due to the following unique advantages. Number 1. Pneumatic eversion to move independent of the environment. Number 2. Flexible feature to mitigate the damage. And number 3. Infinite extension and unlimited degrees of freedom to expand workspace. However, their continuum nature introduces various challenges for modeling and controlling. For instance, their poor controllability restricts their motion to relatively simple path planning, which is not suitable for complex environments. Therefore, enhancing the motion controllability of soft robots is a top priority in soft robotic research. To investigate what their robot can do, the group created prototypes that move through various obstacles, travel toward a designated goal, and grow into a freestanding structure. This robot could serve a wide range of purposes, particularly in the realms of search and rescue and medical devices, the researchers said. The basic idea behind this robot is straightforward. It's a tube of soft material folded inside itself like an inside-out sock that grows in one direction when the material at the front of the tube everts and the tube becomes right side out. In the prototypes, the material was a thin, cheap plastic, and the robot body everted when the scientists pumped pressurized air into the stationary end. In other versions, fluid could replace the pressurized air. Joey Davis-Gray, one of the paper's authors, says mimicking plant movement serves two purposes. First, its length can increase on the order of 1000% similar to a plant. Second, and maybe more importantly, is that if you were to watch a time-lapse of a growing root, its body does not slide with respect to its environment as it grows. This means it can move with ease around environments ranging from search and rescue areas to the human body. Armed with a camera and onboard sensors, the robot can steer through its surroundings free of human control at a speed of up to 22 miles per hour. It moves through pressure as the robot is pressurized. Its tip extrudes new material, so the robot essentially grows. This is called tip eversion. The tip of the growing robot behaves like half of a water wiggle toy and the other half of the robot is fixed at its base, Greer says. The soft robot draws inspiration from the vine growth system. The eversion motion from the tip and asymmetric growth caused by the electromagnet units in the movement system imitates the motion behavior of natural vines to avoid obstacles and trace a target. And the decoupling control and centralized management of the steering actuators in the control system make the movement complicated but coordinated. Therefore, a bio-inspired soft robot combining the growth adaptability of vine plants with a coordinated control system. What makes this robot design useful is that the design results in the movement of the tip without movement of the body. The body lengthens as the material extends from the end, but the rest of the body doesn't move, explained researcher Elliot Hawks, who is a visiting assistant professor from the University of California, Santa Barbara. The body can be stuck to the environment or jammed between rocks, but that doesn't stop the robot because the tip can continue to progress as new material is added to the end. It also has the not terrifying at all ability to fit through narrow spaces, as well as lift or push objects or form a fire hose or radio antennae. Greer says the robot uses the pressure inside its body to lift objects as it grows. The pressure inside the robot itself may be low, but because it comes in contact with a large amount of surface area, it can lift a large amount. A robot with an interior pressure of 3 pounds per square inch, for example, would be able to lift 300 pounds if the weight were resting on a 100 square inch crate. The group tested the benefits of this method for getting the robot from one place to another in several ways. The robot also maneuvered through the space above a drop ceiling, which showed how it was able to navigate unknown obstacles as a robot like this might have to do in walls, under roads, or inside pipes. Further, it pulled a cable through its body while growing above the drop ceiling, offering a new method for routing wires in tight spaces. When it comes to how well the robot can squeeze into the aforementioned tight spaces, Greer says it's a little shocking. One thing we found with this growing robot is that it's surprisingly difficult to stop it from lengthening when it's pressurized. If there's a way it can extend, it probably will, he says. Greer says there's still much more to explore with this type of robot, including tweaking its scale and materials or how it turns. It could help in situations that require navigating cluttered areas from disaster zones to the human body. The paper's authors claim it could even guide a medical catheter. The researchers also hope to scale the robot much larger and much smaller to see how it performs. They've already created a 1.8mm version and believe small growing robots could advance medical procedures. Let us know your opinion in the comment section below. This is all for today. Hope you liked the video. Don't forget to subscribe to our YouTube channel. Stay safe and we'll be back soon with another video.